And we're looking at questions 3 and 4. So you are asked in each row to circle the one with the highest pH. This is page 55, 55. So what we're going to do is we're going to take a look at each substance and decide, is each substance an acid? Is it a base? What is it? So NH4 plus, is NH4 plus an acid or a base or neutral? NH4 plus. And if you don't know, where should you look? You should look on your data table. Okay, so we look up NH4. Here it is, here, whoa, here it is here. Okay, and you can see that is on the acid side. It donates protons. That should make sense to you because remember NH4 is one of the 4 cations that hydrolyze, and cationic hydrolysis is always acidic. Okay? So this is an acid. How about HF? HF is acid. NH3. You guys should know this by this time. NH3 is like one of the most common substances. It's used all the time. It is a weak base. In fact, if we go back to our data booklet, it is the conjugate weak base of NH4. Yes? All right, so ammonia is a weak base. Ammonium is a weak acid. Try and stick that one in your head so it just stays there, because it's something that is just nice to have like in your head rather than having to look it up all the time. Okay, so this is a base. CH3COOH is acid. HCl is acid. So who has the highest pH? NH3. Excellent. Okay. We have a bunch of ions here. And these are negative ions, other than aluminum. So for our negative ions, what are we asking ourselves? We're asking ourselves, does that ion hydrolyze? Does PO4 hydrolyze? Yes, it does. That makes it a weak base. Because remember, anionic hydrolysis is always basic. Because what can this do? Can it donate a proton or accept a proton? It can only accept a proton. How about SO3 2-? That is also a weak base because its conjugate acid is weak, so it will undergo hydrolysis. It will accept hydrogen. Aluminum, there's a cation. Does that cation undergo hydrolysis? Yes, and because it's a cation, that would make it a weak acid. Okay, and it goes via the aluminum hexaaquo, which you can go look up, but it's a weak acid anyway. And then we have CH3COO-. What is that? Does it undergo hydrolysis? Yes, its conjugate acid is weak, so it is a weak base. And finally, Cl-. Does Cl- hydrolyze? No, because its conjugate acid is strong, so no hydrolysis. HCl is strong, So this is neutral. So out of all of our things so far, if we want to have the highest pH, we are looking at the weak base acetate, the weak base sulfite, and the weak base PO43 minus. How will we tell which one has the highest pH? Where will you look? You will look on your data table, yes. PO4, SO3, and sulfite. So we need PO4, PO4. Well, it doesn't matter where the other ones are. There's nothing below PO4. It is the strongest base of all those bases. But if you did want to look at the other ones, acetate is here. And SO3 is here. Okay, so out of those three, PO4, 3 minus is the strongest base, so it has the highest pH. NaCl, acidic, basic, or neutral? Neutral, because Na does not hydrolyze and Cl does not hydrolyze. CrCl3. Does chromium hydrolyze? Yes, because it's feel creepy. Does chloride hydrolyze? No, so we have cationic hydrolysis, and therefore it will be acidic, basic, or neutral? Acidic. NH4I, does NH4 hydrolyze? Yes, it is one of the four, ammonium and feel creepy. How about I minus? No, and since it's cationic hydrolysis, it is acidic. So far, if it were only these three, we'd have to go with NaCl, yes? Because it would have the highest pH. The other two would be lower because they are acidic. Oh, what is CH3COOH? CH3COOH is... You guys are killing me. What is it? It's a weak acid, yeah. And H2S is a weak acid. So we got acid, 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 no hydrolysis. That's going to be your highest pH. Do you want me to do the same thing for number 4, or do you feel like you've got it at this point? Okay, very cool, very cool. Any other questions from anything hydrolysis related? We're good. Remember, when is your quiz on hydrolysis? Friday. What else is on your quiz on Friday? 5.4. But not all of 5.4, and I wanted to make sure you guys know that today. So the quiz Friday is on 5.3, all hydrolysis. And you just reviewed that yesterday. Yes? And that's what we just went over. It is on 5.4, A and B only. So that is mixtures of strong acids and strong bases. The calculations involved with weak acid, strong base, you remember we did one of those yesterday and it was like took forever? Too much work, okay? So we're doing it so that you get a picture of what's happening when you mix them, because that's going to help when we get to titration curves, okay? When we graph the pH versus the volume of titrant added, okay? Yes. What? Oh yeah, go ahead. No problem. No problem. So this is strong mixtures of strong acid and strong base. Okay. But in the meantime, we are going to continue looking at mixtures of weak acid and strong base. And yesterday we looked at what happened when you had exactly half of the weak acid neutralized. This is on page 67. Okay. So when exactly half of the weak acid is neutralized, remember that you still have half of the weak acid left, but half of it has turned into its conjugate base. So those two species are equal. Yes? And that's important, because remember when we were doing indicators and the concentration of the acid form and the base form were equal, then Ka was equal to H+. Do we remember that? Same thing here. When these two concentrations are equal, the weak base and the weak acid form, concentration of H is going to equal the Ka. So when we are halfway to the equivalence point, what is an equivalence point? That's the transition point. It's when all of the acid has been neutralized. The equivalence point, okay? So let's make sure we've got that somewhere. The equivalence point is the point in a titration where the stoichiometry of the equation is perfectly fulfilled. Stoichiometry. What else could stoich stand for? The stoichiometry in the equation is perfectly fulfilled. What does that mean? It means that all of the sample has been reacted and there is no excess analyte or titrant. All of the analyte has been reacted. And there's no excess analyte. And there's no excess titrant. If you don't like those words, you can be like, there's no excess of either reactant. Does that make sense? Okay, so if you're like, analyte, what? All of the reactants have reacted, and there's no leftover of either, would be another way to say that. Okie dokie? Now, if you have a strong acid and a strong base and you react them at the equivalence point, what will the pH be? 7. Yes? Now, since the equivalence point is when all of each reactant has been reacted, the half equivalence point is whatever is in your flask has been half used up. Yes? So that's our half equivalence point. And that's the point where, at the half equivalence point, halfway to neutralization, when half the acid has been neutralized. I'm sorry, what? Yes, it can be. Yes. But we're usually measuring pH because pH meters. But you could easily find pOH, right? Because you just subtract from 14. Yep. Usually the acid is in the flask and the base is in the burette. Not 100% of the time, but most of the time. Okay? Base and burette. Usually, ooh. Thank you, Jade. This tastes great. Thank you. Okay. Would examples 1 and 2 give the same answer if we use the weak base equilibrium? Now let's just go back and see why we were using the weak acid equilibrium. If you remember, we had our formula equation for our strong base reacting with our weak acid. Yes? And we went through and did a RICFA table, and we got some acid left over and some base produced. Yes? Because we used up all of the OH minus. So we ended up with some acid and some base. And now you have the acid form and its conjugate base form, and they set up an equilibrium. We chose the weak acid equilibrium, but you can use either the weak acid equilibrium or the weak base equilibrium, and you should get the same answer. Would we like to prove it? No? You just want to believe me? You're like, it's okay? I'm okay with that. We don't need to. Okay, you could go through and you could do it. You would have to find the KB. All right, so we'll just skip that. There you go. You could do it. It's in the, yes? Okay, because we started with, and this was yesterday, so I don't blame you for forgetting, right? This was 24 hours ago. We started with NaOH and CH3COOH. Yeah? This is a strong base. Strong base reacting with a weak acid goes to completion. Yeah? And then what we ended up with is we ended up with some of this and some of that, and now we have an equilibrium. Does that make sense? So first we have a reaction that goes to completion, then we have an equilibrium set up by the remaining species. Okay? Yeah. And like I said, this is not on your quiz on Friday because this is too much calculations and just kind of gross. Yeah? Okay. All right. So that, I think, is that. Ooh, here we have when all of the weak acid is neutralized. This is on page 70. 70. So we started with some random amount of the acid was neutralized by NaOH. Then we had half of the acid was neutralized by NaOH. And now we're going to have all of the weak acid is neutralized by the NaOH. So what is that called when all of the acid is neutralized? That is our equivalence point. So when we get to the equivalence point, do you guys have any predictions of the pH? 7. Let's find out. Which probably means it's not 7 because I sounded way too excited for it to be 7. So let's see. We have 5 milliliters of 1 molar NaOH. That gives us 5 milliliters times 1 mole per liter is 5 millimoles of NaOH. We also have 5 milliliters of 1 mole per liter acetic acid, which gives us 5 millimoles of acetic acid, CH3COOH. Okay. So we're going to put that in a RICFA table because we have strong base. So that is sending the reaction to completion because we have a strong base. So it's going to be RICFA, not rice. And we are working in millimoles. So make sure if you're working in millimoles, you put that in. Who is in excess, hydroxide or acetic acid? Neither of them. Yes, it is perfectly fulfilled the stoichiometry. The stoichiometry was 1:1, and you have 1:1. So when I talk about the stoichiometry being perfectly fulfilled, if you have a 1:1 ratio and your moles are 1:1, then you have perfectly fulfilled the stoichiometry. You're at the equivalence point. Okay? So how much gets used up? All of it. How much gets used up? All of it, because it's the same amount in each case. So we end up with no moles of hydroxide, no moles of acetic acid. And then on our other side of the equation, we started with 0 millimoles, and now we're going to have plus 5 millimoles. So we've got plus 5 millimoles of what type of substance? What kind of substance is this? That is a weak base. So you have no hydroxide, 0 hydroxide. You have 0, so that's 0 strong base. You have 0 CH3COOH. So that's 0 strong base, 0 weak acid. What do you have this 5 millimoles of? Weak base. That is a weak base. So what is the pH going to be like? It's going to be greater than 7. Okay? If you remember, when we reacted a strong acid with a strong base, HCl plus NaOH gives water. That should be an arrow. Sorry. Water and a salt. And this particular salt, is that an acidic salt, a basic salt, or a neutral salt? That is a neutral salt. There is no hydrolysis. But when we have our NaOH and our CH3COO minus, we end up with, we've got the net ionic equation here, but this would really be NaCH3COO, right? If we didn't get rid of our spectator ions. Is that an acidic salt, a basic salt, or a neutral salt? That is a basic salt, okay? Because the CH3COO minus can hydrolyze. That is a basic salt. Why is it a basic salt? Because CH3COO minus is a weak base. And that's why our pH is going to be greater than 7. So anytime you're doing a titration and you get to the equivalence point, you need to look at who is the salt that got made and say, is that salt acidic? Is it basic? Or is it neutral? What happens in terms of hydrolysis? Do we get acidic hydrolysis, or do we get basic hydrolysis, or do we get no hydrolysis? Okay, so this is why, this kind of thing is why acid base 2 is harder than acid base 1, because there's a lot of things to be thinking about. Yes? A lot of things. You're like, hydrolysis, I got it. Okay, good. Whew. Now let's apply it to this, right? And now let's apply this to that. Oh my God, okay. All right, so we have only base left. And if we have only base, what should we do with our base to figure out the actual pH? If we have a weak base, we should use Rice table and KB. Most of you did that on your quiz. There were a couple people who used Ka. I was disappointed, but that's okay. Happens every year. Don't feel bad. You're in good company. Every year, someone uses Ka. A few people use Ka. It's all right. And then you learn, and then it's okay. All right. So we have only the weak base, so we're going to use our weak base equilibrium. So there's our weak base. It grabs a hydrogen from water, becomes acetic acid, and the water is left as hydroxide. We set up our Rice table. Now, how did I get this number here? Let's see if I actually did it correctly. I had, whoops. Oh yeah, I did. Here we go. Our concentration of acetate ion, our new concentration of acetate ion. We have our 5 millimoles. And that is in a total volume of 5 plus 5 is 10 milliliters. So we get 0.5 molar acetate. So we can put that in our Rice table. 0.5. Two other things are at 0 and 0. Because remember, back up here, we used to have some, we used to have some, and then we used it all up So now we have 0. We used to have some, we used it all up, and now we have 0. We're gonna make more, but that's like stage 2. Step 2, we're gonna make more. Okay, so here we go. We've got plus x, minus x. This part is just like everything we've always done. Assume x is insignificant. Oh, I guess I did that down here, so that's fine. Okay. You're using Kb because we made hydroxide. How do we find our Kb? It is Kw over Ka of the conjugate acid. We find those and we calculate it. We get 5.56 times 10 to the negative 10. We toss that in for Kb. We solve for x squared. X squared is 2.78 times 10 to the negative 10. We take the square root of all of that. And we get x is equal to 1.67 times 10 to the minus 5 molar. Now remember, you need to go back and check for yourself. What is x? X is the concentration of OH. I did have someone solve for X right under OH, and then they said X is equal to hydrogen. It happens, right? Because you're so used to it. You're like, X is hydrogen, off we go, right? But go back and double check for yourself, okay? Just to make sure you don't make any silly mistakes like that. From OH, we can find the POH, and from POH, we can find the pH, okay? And as you can see, the pH is greater than 7 because we took NaOH, we reacted it with CH3, COOH. That went to completion because NaOH is a strong base. We produced NaCH3COO and water. So anytime we have a neutralization reaction and you want to know the pH at the equivalence point, all of this is gone. Don't worry about that. We're not doing that. Nope. I mean, we'll do a little bit of buffer stuff, but it's a little bit different. Okay, so don't stress about it. It won't be like weak acid CH3COOH and weak base F minus. It'll be like CH3COOH and its conjugate base. So you'll only have one equilibrium with the two of them. Don't worry about it. We'll get there. Just hold that thought.
So sort of like right now we're like one strong one.
One strong, one weak. If you throw one weak acid with a non-conjugate weak base, you just get a mess. Okay? Like it forms some sort of equilibrium. What's the point of it? You cannot get to an equivalence point because nothing is driving that reaction to completion, right? And it's just a complicated mathematical mess. I don't even know where I would start. I'm sure I could figure it out, but that sounds like a lot of work. So don't worry, you're never going to have just random weak acid mixed with random weak base. We will have situations where we have weak acid and its conjugate base together, but then we can just use that equilibrium, and that's fine. Okay, so this is all gone at the equivalence point. And all we are left with is the salt. And when you have a salt, what should you ask yourself? Does it hydrolyze? Does Na hydrolyze? No. Does CH3COO minus hydrolyze? Yes. And because it is an anion, that's going to be basic. So anytime you react a strong base with a weak acid, you're going to end up with the conjugate base of the weak acid, which is a weak base, and so it's going to be basic at the equivalence point. So strong base plus weak acid is basic at the equivalence point because hydrolysis. Okay?
I can just think of it as like this strong.
Yes, you can think of it that way, but what if I ask you to explain why? Could you say it's basic at the equivalence point because the base was strong and the acid was weak, and so the base overpowered the acid? I have read this so many times. Is that a good explanation why? No. So if you're doing a multiple choice question and it's like, is the pH going to be greater or less than or equal to 7? You can just say, strong base overpowers the weak acid, therefore it is basic, and it doesn't matter because you haven't explained anything, you've just used that as a little memory tool. Yes? Memory tool is different than explanation. If you were to explain, you would say we produce the salt NaCH3COO, and CH3COO undergoes hydrolysis. I would write the hydrolysis reaction and show that it produces hydroxide, so therefore it is basic. Okay? And don't worry, we have a whole section on this in the titration section. So if you don't get that right this second, you're okay. Okay? We've made it to the equivalence point. Hooray! What if we add more base? Then we have excess strong base. Okay, this is after the equivalence point. So that's going to be when we have an excess of the base. So in this case, we have 6 milliliters of 1 molar NaOH. That gives us 6 milliliters times 1 mole per liter is 6 millimoles of OH minus. We have 4 milliliters of 1 molar acetic acid. So we have 4 millimoles of CH3COOH. Those two react in a 1-to-1 fashion, 1-to-1. So if we have 6 OHs and 4 acetic acids, who is our limiting reactant? Acetic acid is our limiting reactant. So it gets all used up. Okay, so that goes down by 4. That means that the hydroxide, which is 1-to-1, also goes down by 4. So we are left with 2 millimoles, and that's of our hydroxide. We are left with 0 millimoles of the acetic acid. And on the other side of the equation, we have ripped a hydrogen off of the acetic acid, so we're left with acetate. And the acetate started at 0, and it had to go up by because it's a 1 to 1 to 1. It had to go up by 4. So we have 4 millimoles of CH3COO minus. So what have we got in our solution right now? We have 2 millimoles of strong base. We have 4 millimoles of weak base.
This is gonna be basic.
It's going to be basic, yes? And the tricky thing about this is to realize that it is basic mainly because of the strong base. The weak base, it would love to take some hydrogens and leave some hydroxide behind, but its equilibrium is going to get pushed very much to the left, so it's mostly going to stay in its weak base form and not produce hydroxide. We'll look at that in a moment. But anyway, here are our concentrations. So we have 2 molar OH minus from our excess OH minus. That's 2 millimoles in our total volume of 10 milliliters. We got our weak base, but the amount it will produce OH, but the amount it produces will be insignificant compared to the OH from the NaOH. Let's prove it. Here is our acetate ion, 0.4 molar, and we already have hydroxide, which is 0.2 molar. Yes? All right. Plus X, minus X, minus X. Assume X is insignificant. Blah, blah, blah. We found our Kb. Here's our Kb expression. Here's the value of Kb, Kw divided by Ka. All right, so now we have the value of Kb is equal to, and remember, X was insignificant, so we have only 0.2 times X, 0.2 times X, divided by, this X was insignificant, so we just have 0.4. Okay, and we end up with 0.4 times 5.6 times 10 to the negative 10. We end up with hydroxide ion concentration from that hydrolysis equal to 1.1 times 10 to the negative 9. How does that compare with our 0.2 molar OH minus from the excess NaOH? Insignificant. So after the equivalence point, you can just ignore the weak acid and ignore the weak base. Just look at whatever the strong thing is in excess. Okay, so after the equivalence point, all of those pHs and pOHs are dependent only on the strong base in excess. You can ignore the weak base. Insignificant. We're good? How are we doing? Are our brains exploding at this point? A little bit? No? Okay, I got some no's. That's good. Maybe some of you, your brains will stop exploding at some point. That would be good. Okay, so summary. Before the equivalence point, this is AP only, so this will not be on your test. Some of the weak acid remains unreacted. So before the equivalence point, we have some weak acid. That's why it's pink. No, because that's red. I don't know. Anyway, some weak acid has had its hydrogen ripped off by the strong base, and so we have some conjugate base. Yes? So we have some weak acid, we have some conjugate base. Both weak acid and its conjugate base are present. Find the moles of HA and A minus using a RICFA table, where the reaction is a net ionic neutralization reaction. And then find concentration of HA and A minus by dividing by the moles by the total volume. Since both the weak acid and its conjugate base are present, you're going to write the acid-base equilibrium equation, the AB. And then you'll use Rice and Ka to find H plus, or the base acid equilibrium equation. I don't know why you would do this though, because it requires more calculating. You would use Rice and Kb. Okay, what is the likelihood that they're going to give you this question on the AP exam?
0.
Not 0, but slim to none, okay? Slim to none even on AP, just because it's too much calculation. Yeah. So before the equivalence point is AP only. Halfway to the equivalence point is regular. And that's because we can use our little cheating thing, yes? Where we know that at the half equivalence point, HA is equal to A minus, and therefore, when you have your Ka, that's equal to H plus times A minus over HA. And when this is true, this is at the half equivalence point, these two cancel out and you are left with H plus equals Ka, or pH equals pKa. If you forget this formula, you can use all of this nonsense. Blah. So hopefully you remember this one, okay? But it's pretty straightforward. Equivalence point. That's where all of the weak acid has turned into its conjugate base. Only the conjugate base is present. So you find the moles of A minus using the RICFA table. And then you would do a weak base equilibrium using Rice Kb to find OH. Okay? Again, I feel like this is a lot of calculations here, right? So I don't know the likelihood of having it. It's not quite as bad as this one, but it's still kind of yucky. And then after the equivalence point, there is an excess of OH from the strong base. So all of the weak acid has turned into its conjugate base, but the amount of OH from the ionization of the weak base is insignificant. So we just kind of go, ignore that. And so we only use the excess OH from the strong base to find it. And here's the summary of the summary. Okay? No base added. So if we're like at the start, all you've got is HA. Yes? So you would use just Rice and Ka. Make sense? What's so stupid? The whole thing? I wrote this. Oh, the concept. Okay, okay. I feel less insulted now. Okay. Okay. Before the equivalence point, you're going to have some unreacted HA and some has been converted into A minus. So you're going to use Rice and Ka, weak acid equilibrium. At the half equivalence point, you have concentration of HA is equal to concentration of A minus, and you will use Ka is equal to H at the half equivalence point. At the equivalence point, all you've got is A minus only. Right? Because you reacted all the weak acid and it all turned into A minus. So you will use Rice and Kb. After the equivalence point, we have excess OH only from the NaOH. And just take your OH and divide by the total volume, and that will give you the concentration. Yes. Yes. What are the chances of them making you do that? Not a lot. You need to know the concepts though, right? So if you take a weak base and you react it with a strong acid, right? You can say, okay, so I start basic because I got a weak base. And then it's still, before I have excess base or before I have excess acid, it's still going to be mostly acidic, right? Because I've got excess. No. I'm going to go and do it in the notes because I'm just going to say it wrong, confuse you. Okay, yeah. Okay, blah, 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 blah. All right. Whew. Oh, did I not do the other way around? Oh, that's okay. We're going to make our own notes on that. Okay, so what if we had a weak base plus strong acid? Okay, so now in our flask, we have our weak base. And in our burette, we have our strong acid. So before we add any acid, what's the only thing we've got? We got our weak base. Let's call it NH3, for example. So how would you find the pH? You have a weak base. How do you find the pH? Rice and Kb. Just like you did on the quiz. Yes? You're given a weak base. Before you add any acid, you've just got weak base. Yes? Okay. If we have some acid added, what are the species that we have present? We have the weak base and we have its conjugate acid, right? So we're going to have its weak base plus conjugate acid. So for example, that could be NH3 and NH4 plus. Okay, but it is still going to be basic. We'll use rice and KB. Although you could use rice and Ka too if you wanted to. Because you got both of them. You could use... You just have to make sure that if you use rice and Kb, that you have your reactant being NH3. And if you're using rice and Ka, you would use NH4 as the reactant. And if you're like, I don't know what's going on, don't worry about it, you won't have to do this. Okay? This one here is like the one where I think, probably don't care. Do you know what I mean? Like, I think it's unlikely to come across. Certainly, I'm not going to give you a question like that. Okay? Then we have, at the half equivalence point, what do we know about our weak base and our conjugate acid? We know that the moles of weak base are the same as the moles of the conjugate acid. So for example, the moles of NH3 are equal to the moles of NH4. And you can use either Ka or Kb. I would use Ka because it's easier. Let's say we were doing NH3, it would be NH4, or sorry, if we did Ka, it would be NH3 times H3O plus over NH4 plus so you could do that and you could say, all right, these two are the same. So what do? They cancel out. Our concentration of NH3 is the same as our concentration of NH4 plus. Okay, so at the half equivalence point, Ka is equal to H3O plus. You could also say, let's say we didn't use the acid form. Let's say we used the base form. NH3 plus water in equilibrium with NH4 plus OH minus. That would give us Kb is equal to NH4 plus times OH minus over NH3. But remember, these two are the same. So what are we left with? Kb is equal to the concentration of OH minus. So this is the, and we'll put a little half down there because it's that's at the half equivalence point. And we'll put a little half down there because that's at the half equivalence point. Yes? Whew. At the equivalence point, we will have taken all of our weak base and converted it into weak acid. The weak base will be all gone. Yes? So because we have a weak acid, it will undergo hydrolysis. Yes, yes? Okay, so you'll use rice and Ka. And it's going to be acidic because all we have left is a weak acid. Strong base plus a weak acid, weak base gives weak acid. This is all gone. Yeah. Okay. And then my favorite one, after the equivalence point, we stop worrying about all this nonsense and we just say it's just the excess strong acid. Yes? Which is so much less work. There's no Kas, there's no Kbs, there's no nothing. Okay? After the equivalence point, only the excess strong acid matters. Yes? Yeah? To be honest with you, all of this calculation and everything here, shake it off. Shake it off. If you understand it, if you feel good with it, that's fantastic. If you feel like kind of iffy with it, that's okay. Because we're going to look at the titration curves in a more holistic manner. Yeah? And we're just going to be like, when you have a weak acid, the pH starts about here, and then it goes up, and then it goes up, and then it goes up, and that's all that happens. And you'll be like, it's an S curve. And the middle part of that straight up and down point is going to be either at 7, above 7, or below 7, based on whether it's strong acid, strong base. And you can just memorize those. You can be like, strong, pH is 7 at equivalence. Strong, weak, it's either going to be above 7 or below 7, depending on whether the strong thing was the acid or the base. So don't freak out about this. Chances of you having to do explain, calculate. Don't worry. So just be like, get the big picture. Okay? And don't stress. I think that's it for today, yes? So we are going to assign you guys the questions in 5.4c. Oh, no. 5.4b. Because that's going to take care of the second part of Friday's quiz. You did the hydrolysis stuff yesterday. You are doing the mixtures of strong acids and strong bases today. So that's part of Friday's quiz as well. So you'll have done both. Hi.
You wrote strong base.
Oh, I should have written strong acid here. This should have been strong acid. There we go. Yes. you won't have to calculate the pH. You'll just say above 7 or below 7, predominantly acidic.
So just to find the predominant reaction?
Yes. Yes. You will not be required to calculate an actual pH. If you're calculating an actual pH, it'll be for something that is not amphiprotic. Okay? Thank you guys so much. I know that was a lot.